just be aware, of course, if you speak, then that will be part of the recording. I'm happy to have you speak, but just so that you know that you're being recorded, and that would then be posted in Canvas. Okay, also I will sort of look back and forth while I'm doing this into the chat to answer questions. You can feel free also to raise your hand. It's sometimes hard for me to notice something comes into the chat when I'm looking at my writing and thinking about what I'm saying. And so I will do my best, but I might miss something in the chat. Now I see that Benjamin has posted a question, technical MATLAB question here. Oh, so yeah, so you're talking about the little x and y, is that correct? Yeah. Okay, so what you want to do is, I'm just going to take a quick look at this before I start. Little x and y. So what is that? Is your grid size, like, so your x and y, like your axis is going from 0 to 15, 20 to 100, and 20 to 100. So your mesh grid is going to be a vector that contains like what you're choosing. Like for example, let's just see here. I'd have to actually take a look at the command. So, but basically, what you want to be doing is indicating how fine you want to make your steps. So, like, does MATLAB want to evaluate the function every 0.01 and make a dot, or does it want to do it every 0.001 or 0.1 or whatever? That is your mesh size. So just go, if you go help mesh grid, see what I think X will be and Y will be. I'd have to do that, but take a look. I believe that X and Y will be a scalar. It's just telling you like how fine the mesh should be. Okay. If it's a vector, then you enter that yourself, like, you know, whatever, 20, 20.1, 20.2, 20.3, using some sort of a loop. But I suspect it's going to be a fixed grid. And then that creates the two vectors for you on which points to plot. Okay. All right, let's start with the topic for today, which is diagonalizing symmetric matrices. So we've seen how to diagonalize any square matrix. So I just want to sort of suss out where we're at. We have had the idea of how to diagonalize a square matrix. We had some sort of just any old n by n square matrix. We could diagonalize that. We were calling this guy A, and then we had a procedure where we could find P such that this worked. That was diagonalizing any square matrix. That, of course, will work if the matrix is symmetric. It works for all, it'll work for symmetric ones. However, symmetric ones have some nice properties which make them faster to diagonalize. So that's next step 2. We're gonna see a matrix like this, which is symmetric. And I'm putting this line here to indicate that there's reflective symmetry across the main diagonal. Okay, that's the type of matrix where A equals A transpose. That's a symmetric matrix. First off, just want to reiterate, this method will work for all matrices that are square. This method is going to work for symmetric matrices, and it's what's nice about it is it diagonalizes this way. So you have this nice feature that you don't have to find an inverse. Okay, you just simply find P, and then you take the transpose, which is basically almost an instantaneous calculation, and then that makes things easier for you. So noticing something's symmetric when you diagonalize it is useful. Okay, that's the next step. And then just to see where we're going for our final topic on Friday, what we're going to do is we're then going to have matrices that are not square. So those ones will be not square, and we still want to kind of get the idea of diagonalizing them. So we're going to have to then get something else because these two procedures won't work for non-square matrices. So this is the not square. Okay, that's our final. That is going to be our final topic on Friday, and that we're going to call that. It is called the singular value decomposition. Okay, so let's now go here. for diagonally symmetric matrices. It should be, this lecture should be relatively straightforward if you got the diagonalization earlier, because it's just a little bit of an extension or a little bit of detail based upon that. Okay, so we have a reminder, what is a symmetric matrix? That's where the matrix is equal to its transpose. And then there's these important features of symmetric matrices. First of all, they're always diagonalizable, unlike these guys, which sometimes didn't diagonalize. Okay, these guys are always diagonalizable. So that's also a nice feature. Then these two things here, all symmetric matrices have real eigenvalues, and this is what allows this change, that if you have a symmetric matrix, the eigenvectors are orthogonal. So that's a nice feature. Okay, so let's just remind ourselves an example here of symmetric matrix. That is this thing here. If we have a matrix like this, there's two ways of sort of looking at this and seeing if it's symmetric. I often just sort of draw a line on the main diagonal and say, you know, if I folded it on half on that guy there, would the two end up on the two, and all the other numbers for that thing. The other thing to do is to write the transpose, and you take the first row and make it the first column, second row and make it the second column, like that, and you're like, oh, it's equal. Okay, so then it's diagonal. Similarly, let's just take a look at another matrix, a little bit bigger one, 3 by 3. Which one did I use here? 2, 1, 2, minus 1, minus 2, minus 2. Okay, there it is. And again, I'm just going to go like that, and then I'm going to notice these two are the same. These two are the same. And oops, something is wrong. Not symmetric. Let's put a minus sign there. Now it's symmetric. Those two are the same. Okay, so that's now that matrix is symmetric. Both of these are examples of symmetric matrices. Okay, here's a question for you guys. Are symmetric matrices always square? Yes or no? Yes, thank you. Quick answer on that. Yes. Okay, there's no way to be equal to your transpose if it's rectangular, because the dimensions won't even match up properly. Okay, so now we're going to do and take a symmetric matrix, and we're going to basically do a review. We're going to use the method that we had from before. So this will be a nice review of that method. And we're going to diagonalize a matrix. This guy here, it is symmetric. Here it is. Yeah, okay. And so diagonalizing it means finding P such that P inverse AP is D. So usual thing, I need to find the eigenvalues. So I'll take the determinant of lambda I minus A. And that is the determinant of lambda I minus A, like that. That determinant is lambda minus 1 squared minus 9. Okay, admittedly, there's a little bit of algebra here. Please check my algebra. But you expand this and combine the like terms and then factor. We've done this numerous times. Clearly, this is something that you need to be able to do. Finding eigenvalues and eigenvectors is coming up in a lot of applications. Okay, so here we are. Then we find that lambda 1 is minus 2 and lambda 2 is 4. It doesn't matter which way you label them. We will see when we do the singular value decomposition, we actually want to order them in size from biggest to smallest. Okay, so then I find the eigenvectors. That is going to be for lambda 1, the eigenvector. I will find it as 2i minus a. I'll be finding the null space of that, and that looks like this: minus 3, 3, 3, minus 3. Okay, so that is putting in minus 2 for this guy here. And I'm going to row reduce, getting this 1, minus 1, 0, 0, 0, 0, finding that the first eigenvector is T1, 1. Okay, similarly, do the same thing for the second eigenvalue, and that is going to be then the reduction of 4i minus a, like that. So now for that value here of lambda, I am plugging in 4, getting 3, 3, 3, 3. A very nice Very nice matrix to row reduce. Then I get the second eigenvector right there. Okay, that allows me to suss out that P, that is this matrix right here. P is going to be the eigenvectors of A put into P as columns. So it looks like that. Okay, then I take the inverse of P and I get 1 over the determinant, and I get here the 1 swapped places, but you can't tell, and like that. Okay, so that's the inverse matrix. I often find if I'm going to be multiplying out, easier to write it like this. Okay, there it is. So now if I haven't made an error, I will multiply this out. I'm going to answer that question, Dat, in 2 seconds. You have a minus on the top left. A minus on the top left. Uh-oh. Not seeing what I'm being told. Oh, okay. So it's just a square bracket. Oh, I see the problem there. Okay. Yes. Yeah. There. Okay, good. Okay, so let us just recognize here that then P to the minus 1 AP, which I can write out, P to the minus 1, 1/2, 1/2, minus 1/2, 1/2, A, 1 minus 3, 1, and then P, 1 minus 1, 1, 1. Okay, I can perform this multiplication, and but if I'm short on time, or I am right, what I would do, like for what I'm saying here is on an examination kind of situation, I would write this down immediately, because I know that it's going to be a diagonal matrix with the eigen values on the diagonal. Now you can yeah, so what I see that question, William, which is can you write this and not solve? Why not just write down D, right? Because you can write it down, and by not doing the multiplication anyways, you know what it has to be. That would be my approach on an exam. I would write down P to the minus 1 AP, and I would put it equal to D, because you want to know what D is actually, because we're going to use D, like for example, where we later, like if we're here, P to the minus 1 AP is equal to D, it is the case then, of course, that P to the minus 1 is equal to A. And then we saw how to use that, which was like, for example, if we wanted to take the 100th power of a matrix, we could take that as PD to the 100, P to the minus 1, like that. And then this is really easy to do. Like in the case that we have D here, it would just be minus 2 to the 100, 0, 0, and 4 to the 100. So this allows us to get the powers of matrix easily. So in that sense, you should identify what D is. If I was doing an exam, I would compute P. I would compute P inverse. I would write this down. And then I would write this down because I know that's what it has to be. And then I would go to the next question. And if I had time, I would come back and multiply these 3 matrices and make sure it was this. If it was not, I would go back and say, okay, there's an arithmetic mistake somewhere, right? So you get a chance to check it in a different way. Okay. Then there was a question. So the question, Gary, I'll just get your question first, and that is, do we need to calculate P if you're asked to find D? Yes, you do, because I mean, you do know that D is going to be the eigenvalues, right? So, but the typical thing would be find the matrix P that diagonalizes A. And if you're going to be using this in any way, it is true, you know D without even finding the eigenvectors, right? But if you're going to use this in any way, you're going to have both of those guys sitting there. So a typical question would be, find the matrix P that diagonalizes A. Or find a to the 5 or something like that, or maybe making it so that you for sure can't try to multiply it out. Find a to the 1000. Then you would have to find p to the -1, and d, and then write out the multiplication and actually find the 100th power of the matrix. Okay, so the other question was, does it matter if the order does the order matter? So here I chose, this question has actually come up several times, and so that's fine. Let us just see that I called this guy lambda 1, and I called this guy lambda 2. That would be the other order, right? Then this guy instead would be V1, and this guy instead would be V2. And what would happen? What would happen is P would look like this, V1, -1, 1, and 1, 1. That is not the same P as I had before. The columns would be in a different order. That's fine. So that would be P, and then D would be this guy. D would be lambda 1, which was 4. It would be 4, 0, 0, -2. Okay, so the order doesn't matter, but if you chose to do your eigenvalues in a different order, then the columns of P, the eigenvectors, are different. So it has to properly line up. This eigenvalue right here has to line up with that eigenvector, and this eigenvalue lines up with this one. And you'll see that's the case over here too. Like if I look back here, in this case, this is the eigenvector for -2, and this is the eigenvector for 4. And you'll see it's the same. Okay, so that goes together and that goes together. They both have to be done. It doesn't matter. And so that actually, so if you're just going to write out D, make sure you don't do it in the wrong order, right? Like if you've written out P like that, you just wrote it out, you don't do the multiplication. Make sure you don't backwards these things up, right? Because it does matter. It has to match with the order that the eigenvectors went in there. So I did actually say that you don't have to have the largest eigenvalue as lambda 1 if you don't want to. What is nice about that is that when we're going to do the singular value decomposition, that is what we're going to do. So there are some applications where you want to order the eigenvalues in order, and we have already touched a little bit on the fact that there's a dominant eigenvalue and a dominant eigenvector. And so sometimes for applications, it's nice to see the dominant, the dominant eigenvalue first on the upper left corner, and then they sort of go down as you go along the diagonal. For this, it does not matter. And we're going to see with our last topic, singular value decomposition, what's going to happen is we're able to do that. We're going to do it's a type of diagonalization for rectangular matrices, basically, and we're going to order them, the eigen, what are their singular values, which are equivalent to the eigenvalues in a rectangular context, and we're going to order them. And what we're going to see is if you have an image on your screen and you decompose the matrix that captures all the information about that image, and then you throw out all of the information except for the information about the image that corresponds to the dominant eigenvector of a dominant eigenvalue, you have way less stuff to store. You lose a bunch of information, you have a lot less stuff to store, but you don't. Sometimes the picture looks pretty good, and then what you can do then is add in the next dominant, like sort of the second biggest eigenvalue, and you get the picture sharpens, but the picture is not exactly 100% unless you have them all. But each time when you add the information pertaining to a different eigenvalue, which will be called a singular value, you get less and less. And so you actually can so what you're doing is figuring out how much information can I toss out and still recognize the picture, and if that matter, still have a fairly good picture. And so this is a method of doing image compression. So what you do is you have all this information from some camera image or something like that, and you don't want to store all this stuff, or you don't want to like transfer large files like this. What you do is you do a singular value decomposition, and then you're like, okay, I'm going to keep the first three, the first three dominant things, and we're going to be able to visually see this on Friday, and then I transmit the rest. I save like a huge amount of storage and transmission doing that. This is a type of image compression, and then there's like one that you're aware of, at least by name, that maybe don't know how it works, but is the JPEG image compression. So you take a picture with your camera, you can have with your phone, you can have a raw file typically, which is full all information, especially if you're using a digital camera, and then on your iPhone or even with your digital camera, you can say use a JPEG format, and that makes some loss of information, but it enormously makes the file sizes smaller and easier to manage. And so long as you don't lose too much so that the image still looks good, nobody seems to care, right? Everybody's happy and you've got a lot less storage. So that was my reasoning for saying you can get the idea of ordering them, because at some point it does become important. And if you're always ordering them in one order, when it doesn't matter, it doesn't matter. And when it does, you're already doing it that way. Okay. All right. So let's just say a few things here about the eigenvectors of symmetric matrices. A symmetric matrix has distinct eigenvalues, and the eigenvectors are orthogonal. If you normalize those orthogonal eigenvectors, you get if you normalize them, then they become orthonormal. They're of length 1. So that is orthogonal plus of length 1. Okay. And then if you stick those orthonormal eigenvectors into a matrix, then you get an orthogonal matrix. The orthogonal matrix has the columns being orthonormal. Okay. And then we call A and B orthogonally similar, and they related like this, where this is no longer p to the -1, it's p transpose. Okay, so but it is important that this matrix P is orthogonal. So that means the vectors will be orthogonal, the eigenvectors will be orthogonal just based on the fact that it's a symmetric matrix, but we also have to make the eigenvectors orthonormal. Then we do not have to find an inverse. So let us do an example here, and then I'll see if you've got questions. So here we've got we got things saying orthogonally diagonalize. Okay, that's a clue to check, because it's not going to work if it's not, that the matrix is symmetric. Okay, so that is the case here. The matrix is symmetric. So now we proceed along with the same diagonalization procedure as we had before, and that will then be, we'll take the determinant of lambda I minus b, and that looks like this, the determinant of lambda minus 5 minus 2 minus 2 lambda minus 2. Okay, now I'm just going to write out what that is directly. We've done this a zillion times. Make sure you can do this. So there are two eigenvectors. I'm going to not do what I said. I'm going to make them from one to the other like this. Doesn't matter for this procedure. Okay, so then I calculate the eigenvectors for each one of these. So that is here, this 1 times I minus a augmented with 0, and then 6 times I minus a augmented with 0. I row reduce those two guys. And in this case, I want you to check my computations here. It's a good exercise to do. This is what I got. And then that gives me a first eigenvector of this guy here. And here I get like that. I get a second eigenvector of this guy here. Okay. All right. Now, let's just check to make ourselves happy. We just did this procedure on a symmetric matrix. I've been telling you, and it is true, but we will check. Are these guys orthogonal? If you know the matrix is symmetric, and you go ahead and find the eigenvectors, it's sometimes very quick to look and go, are they orthogonal? If they're not, you know there's an error. like you have that error detection system running in the background, everything that you can bring to bear on the problem, even if you don't actually have to do those steps, is useful for catching errors. So in this case, I wouldn't probably write this down doing this problem, but I'd probably do this in my head. I was going to say, okay, are these guys orthogonal? And be like, okay, that means minus 1/2 t t dot 2t t. What is that equal to? That is t minus t squared plus t squared. That's equal to 0. Tick. They're orthogonal. Okay, so the eigenvectors came out to be orthogonal. So I at least have a little bit of confidence that I haven't made an error yet. And then this step is what we did not do before. So this is a new step if we're going to orthogonally diagonalize, we need to get an orthogonal matrix. The columns have to be orthonormal. So that length has to be 1. So I'm just going to put that here. We normalize. So I take the norm of the first eigenvector and I get square root of 1/4 plus 1. Okay, I'm doing this guy right here, and I get root 5 over 2. And then I take the norm of V2, that's this guy here, and I get the square root of 2 squared plus 1 squared, and that is 5, square root of 5. Okay, so then I rewrite V1 in this manner here. Like this, I multiply by, sorry, I divide by this right here. So I'm taking here minus 1/2 divided by root 5 over 2, and I'm taking 1 divided by root 5 over 2, like that. And that works out to be minus 1 over root 5 and 2 over root 5. So that this vector here, again, you can quickly check, is the norm of that vector 1? And it is, so that at least there's not been, that doesn't mean no mistake, but at least there's some mistakes being ruled out. And then I do the same thing with V2. I take the V2 vector 2 and I divide by the norm of V2 root 5, and I take that guy 1 and I divide by the norm, like that. Okay, so I've got V1 and V2. That now allows me to form P in the same way that I did before. Now I'm back to the procedure that was before. This new step has been to normalize the eigenvectors. You'll notice actually, if you're using MATLAB to check your work and you ask what is the eigen vector, it just normalizes automatically. It just like picks this whatever value, it picks it picks a value of t, it picks the value of t, in fact, that normalizes it, always gives it to you normalized. Okay, so here's P then. P is the columns, minus 1 over root 5, 2 over root 5. That's this guy right here. And then the second one is 2 over root 5 and 1 over root 5. And that's this guy here. So that's V1 and V2. Now, the nice feature here with the symmetric matrix is that I don't have to now take an inverse. I now maneuver along, and the inverse is the transpose. So I can just write this here like this. So I save actually finding an inverse is actually a computationally expensive procedure. So this is this is a nice feature. Okay, so I got a thing here. Shouldn't V2 be 1 over root 5, 2 over root 5? No, I don't think so. Because this is 2, 1. And this is a root 5. This is the length right here. V2 has this length. Yeah, I think you might have accidentally used this length. I can see the confusion there. Yeah, okay, yeah. I got to use the length. So I'm taking here V2 divided by the norm of V2. There. Okay. So now I write that out. Minus 1 over root 5, like that. Minus 1 over root 5, 2 over root 5, 2 over root 5, 1 over root 5. That is P transpose, which is, hang on, P transpose, let's see. Yeah, so P transpose is P. Okay, and then there's B. the matrix we started with, and then there's P, it's 1 over root 5, that they were, this doesn't actually have to happen. This is a coincidence. They're the same. Okay, and then when I multiply those guys together, which you can do, the same thing happens. I will get the eigenvalues on the main diagonal, and that is my matrix D. So the difference is right here. That is the difference from what we did before. And then this thing here, the normalizing. Those are the two differences. Yeah, exactly. Thank you, Najwa. Exactly. That is where we're at. That is the key thing to see. Why did you use the transpose instead of the inverse? Now, if you use the inverse, you'll get the same thing, but you'll waste a lot of time calculating it. You can always use the inverse because that works for every matrix. But for symmetric matrices, that's the transpose. So it's a much nicer situation. Okay, so that is the diagonalization of a symmetric matrix. It's going to be apparent why we did this on the lecture on Friday, which we actually might be able to start today. Let's see, it's 12 o'clock. We'll see how we do because we're getting close. This is a fairly short lecture since we've already basically covered this. Okay, so now we're going to be I've got a couple of 3 things we're going to state here without proof. And actually this thing here called the principal axis theorem. The principal axis theorem is this guy. Of these 3 statements, it's this guy here. Okay, so let us just say we've said this actually a couple times already today. Always worth remembering. If you got a symmetric matrix, the eigenvalues are real. Let's just leave this one aside for a sec. We're not really using that. And then here's the one that we used. And it goes in both directions. So this is a if and only if. So if the matrix is symmetric, then it's orthogonally diagonalizable. If it's orthogonally diagonalizable, then it's symmetric. That is your necessary and sufficient situation. Okay, so before we leave this topic, I'm going to just go and orthogonally diagonalize a 3x3 matrix. This is just takes up a little bit more time. I am going to leave out some of the algebra steps in calculating the eigenvalues, like the roots of the characteristic polynomial. I also going to leave out some of the row reduction because we've been doing that throughout the course. So here we go. This is I'm going to orthogonally diagonalize this. So I do a quick check. Is it symmetric? Okay, I could write B transpose here. First row, I'll put as the first column. Second row, I'll put as the second column. Third row, I'll put as the third column, and then I'll see if they're equal. Okay, they are equal. So this is a symmetric matrix. So I know that I don't have to compute an inverse. So I go ahead with the usual program of finding the eigenvalues, and I write that the determinant of lambda I minus B. There it is. And like I'm going to do a cofactor expansion along the first row. Let me just, I'm going to write out just this detail, and I'm going to stop writing out all the details because this is, there's the cofactor expansion along the first row. Then you, of course, you know how to take the determinant of these 2x2 matrices. Then you got to multiply by that. Then you got to collect all the like terms. And then you get the characteristic polynomial, which I got to be this guy here, lambda cubed minus 4 lambda squared plus 3 lambda. So that's the characteristic polynomial. You factor that. There you go. And then you get the eigenvalues like this. Lambda 1 is 0, lambda 2 is 3, and lambda 3 is 1. Okay, then, so that's the usual part of the program. Find the eigenvalues, then we find the corresponding eigenvectors. Okay, you'll notice we're immediately kind of running our error detection software, and we're like, okay, symmetric, all the eigenvalues are real. Okay, that happened. That's good news, right? If you try to factor and you got a complex pair of eigenvalues, then you should go, oh, something's wrong. That doesn't happen if the matrix is symmetric. Okay, so now we're going to, for each one of these, we're going to find the corresponding eigenvectors. Let me just expedite that by writing down what they are, and plus normalize, make them of length 1. Okay, so that's going to be like this, minus, oh, sorry, it's not a minus, it's 1 over root 3 minus 1 over root 3 and 1 over root 3. That is the eigenvector corresponding to lambda 1 equals to 0. And then we have V2, and that is minus 1 over root 6, 1 over root 6, 2 over root 6. And I got V, when I did this, I got V3. So you can check this with MATLAB. That is highly effective, highly quickly effective to make sure that you are doing what you're doing. Also, we expect this situation, which can be a check on your work. We expect that the dot product of that is equal to 0. The dot product here is equal to 0. And the dot product here is equal to 0. All three of those dot products have to be equal to 0. Okay, that situation is in place. Then we can write out the matrix P, and it is an orthogonal matrix, meaning the columns are orthonormal and they corresponded to the eigenvectors. And we can also write out what is D. That is the matrix with the eigenvalues in the same order that we put the eigenvectors in on the diagonal. There. And of course, you could then write out P transpose AP equals D and confirm that. It's just more work, that's all. All right. There's one thing I have left out here. I'm going to be honest about it, but I'm not going to ask you to do this. This kind of a question won't come up for you. But we're omitting the case where there's omit the case where there is a repeated eigenvalue. We've omitted that. So if we got a situation where we had lambda 1 is equal to 2, lambda 2 is equal to 2, then lambda 3 is equal to 4, say we had that case like that, then we would, of course, only have 2 eigenvectors. And then what would we put in here? Right? We'd only have 2 columns, and we would need a third column. And because we did not cover the Gram-Schmidt procedure, we actually don't know how to do that, but there is a way of saying, okay, I've got this guy, and now I need another one. And what you do is you find the one that's orthogonal to the other 2 and spans R3, and you put it in there, and everything is fine. It's not that it doesn't work, but we haven't really put a lot of emphasis. We did not do the Gram-Schmidt procedure, so you're not gonna see a case where this happens. We're just gonna, but I'm not trying to put it under the carpet, right? It's still there. Okay, so that is diagonalizing a symmetric matrix. Does anybody have a question they want to ask about this? Because we've got about 12 minutes, so it's quite nice. We can start the singular value decomposition, which is a little bit more tricky than this. Any question with this before I change to that? Okay, I'm going to do that. And then what I'll be able to do next on Friday when I see you, hopefully the snow situation will be such that I will be there on Friday. I suspect it will be. And then what we can do is we can start the class by seeing how you use this stuff, because that's pretty cool. And then we'll have already done a little bit of the theory, and then we'll finish off the theory. Okay, so here's the basic situation. We've so far, when we've been doing this diagonalizing situation, we've been diagonalizing. What do we do when the matrix is not square? That's the basic issue, because many matrices, including if you think about the way your aspect ratio is on your screen, or you've got a picture, they're usually not square. And they're in fact usually diagonal. I mean, they're rectangular, sorry, they're rectangular. So I mean, if we're talking about a matrix that captures what's on your screen or a photograph, it's not square. And so now if we want to understand how to sort of manipulate this thing and having a useful factorization so that we can do that, we can't just diagonalize anymore. Like that's out the window because it's not square. Okay, so what we're gonna see is a slightly different procedure, but the idea is actually pretty similar. And so we're going to introduce this new term here, singular values. And the singular values are the square roots of the eigenvalues of A transpose A. That's what it means. So if we have a matrix A, we take the product A transpose A, then we find the eigenvalues of that, and then we take the square root. We call that the singular value. You can see that that's just about like an eigen value, because you're taking an eigenvalue of something that's like a square, like A times A, and then of course you take the square root. So this is a way of getting what's equivalent to an eigenvalue for something that's rectangular. Okay, and when we write these three letters, SVD, that stands for singular value decomposition. Okay, and so that is a decomposition of a rectangular matrix into the product of three other matrices. Okay, which thinking about it, our diagonalization, that was our diagonalization, where we then could write this. This here is a decomposition of this matrix A into three other matrices. It's factoring A into three other things. For example, 30 is 2 times 3 times 5. There, that's a decomposition of 30 into three factors. It's the same idea. Okay, decomposition of a matrix into three factors. Okay, next thing to notice, well, we are in fact already said this in this lecture here, but let's just repeat it. Okay, a symmetric matrix, it has this feature, A transpose equals A. That immediately tells you rectangular matrices are never symmetric. Never symmetric. Never symmetric. Okay, there's that. Okay, now let's take a look though at a rectangular matrix and its transpose. So imagine that I have a rectangular matrix. There, M not equal to N. Okay, then I am going to consider this product A transpose A. There, I'm going to take the product of A transpose A, and I'm going to take the transpose of that product. So be thinking of this as a kind of a bit of a blob, right? That's some matrix. Let me just ask you something. Is that matrix square? A transpose A, is that square? Yes, it is, right? That all is fast. Okay, yes. So that's the thing to notice. A transpose A is square, right? Because you're always like this. A transpose will be N by M, and A is N by N, like that. These two match, and the result is an N by N. Okay? It's always square. Okay, so we've got a square matrix. We're taking the transpose of it, and we use that little law of transposes, which will then say this is A, that's this A transpose times A transpose transpose, like that, and that is A transpose A. So we have, via that little observation, that we have that the transpose of this thing is equal to itself. That tells you that this thing is symmetric. Okay, that means that A transpose A is symmetric. So not only is it square, it's square and symmetric. So A transpose A is symmetric, and you can use a similar exact argument to show that A transpose is also symmetric. Okay, so let's just do an example so we can see that highly exciting feature. And let's just take a matrix here, A, looking like this, 1, 2, 1, a rectangular matrix. Okay, let's multiply it by its transpose. Like that, and we get this guy, 6, 2, 2, 5. Okay, symmetric. Okay, so now what we can think about is we have A, which is rectangular, which we can't diagonalize. We multiply it by its transpose, we get some other matrix. Now we're in the situation where we already know how to orthogonally diagonalize A transpose A. Okay, so what we do is we adapt our method from before, basically, right? We're like, hey, we couldn't orthogonally diagonalize a rectangular matrix, but we notice that if we take that thing, multiply it by its transpose, we get a symmetric square matrix, which we can orthogonally diagonalize, and then we feel happy because we can do something. We adapt the method from before. Okay, so now we want this. So we're thinking of this procedure that we had for the. We're thinking of. Okay, here's how I want to put it. If we're here asymmetric, that means of course it's square. We had this idea, right? We had the P transpose A, P equals D. Okay, so now we're thinking, okay, we don't quite have that. So we're gonna instead try to get something that looks like this. U transpose A, V equals sigma. Okay, so this is the original A here. It's not A transpose A. And we're going to try to find the transpose of a matrix and a matrix, and it's going to be equal to something that's sort of akin to a diagonal matrix with the eigenvalues on the thing. So we're kind of trying to line it up the same as it was before. And what is different is that in this case, this was the same matrix. We can't do that because we have a rectangular matrix. So we're loosening some of our conditions here. We're like, okay, this matrix, this one will be the transpose of some matrix, but it won't be the transpose of this matrix. We're going to allow those two things to become different. Okay, so I'm going to just write what we want U and V to be. We want U and V to be orthogonal, but they will not be transposes of one another. Okay, so that's the thing. So they are orthogonal. So we have this feature. Okay, but they're not. It is not the case that U is V transpose. Yeah, don't get confused yet, Martin. Not confused. It's not just a notation. What we're doing here is we're going to have a matrix here that I'm calling it sigma. I'm not calling it D. Okay. Normally this has been previously called D, right? And it was a diagonal matrix. Diagonal matrices they're square and they look like this. There's an eigenvalue here, whatever, like that. They're square. We're now moving out from square land into rectangle land. And this thing here will not be square, not square. But it will still have the concept of a diagonal. Let me just maybe even give a thing over there. It'll still have the concept of a diagonal, like I could have like this. I'm going to call it like this, in fact, sigma 1. There. Kind of have the concept of a diagonal, but not quite. Right? It's not symmetric, but you can still kind of do this. And these guys here are not eigenvalues exactly what they are of A. What these guys are going to turn out to be are the square root. We're going to see this coming. There's no way you would know this yet. Square root of the eigenvalues of A transpose A. So we're using a different notation, So your answer was just a notation is quite correct. What we're saying is we are still going to end up doing a decomposition of A into three things. And we're going to do it like this. So D sigma is like D, and it's going to contain the singular values of A. And then we've got these other two matrices, U and V, which are akin to P transpose and P. Okay. All right. So if I say I'm going to try to do this procedure, then I can multiply on both sides, and I can in this manner. So these are now three matrices like that. If I can figure out what U and V are and what sigma is for that matter, then I can decompose A. This is like going from here to here is just solving for A. Okay, solving for A. I can decompose like this. And then I could also here take the transpose, and I would get like that, transpose, and then I would have A would be equal to this. So I have decomposed, I will, once I figure out how to find U, V, and sigma, I have decomposed A into three matrices, and I can decompose A transpose also into three matrices like that. Okay, so that is going to be our idea of what to do. That is the basic overview. We'll start on Friday to do this in detail. We'll do it in an example, and then we'll see how the image compression looks with this technique. That'll be on Friday. Okay, I'm going to have to run off because I have to let this recording, whatever it does, render at the end of this thing, and I have to start my next lecture in 9 minutes. So I'm going to run off. I will be there obviously on Friday, and I'll have my office hours tomorrow afternoon as well, like usual. So if you've got other questions, please come to those. Thanks very much for being here, guys. See you on Friday.